Hello, this is Aaron from Chef. In this video, I'm going to show you how create and use Atoms Behavior tree on your agents. So let's create an Atoms Behavior tree asset. From the Atoms CRUD menu, create an Atoms Behavior tree. Let's call this PT Atoms. Now let's open the behavior tree. This is a standard behavior tree, so you can create a composite, decorator, and task nodes. If you're not familiar with behavior tree, the behavior tree is a graph that is computed by every tick, and it's composed by multiple nodes. Every node, some nodes can have children, so they basically execute children. Some other nodes, there are tasks, they just do things and return a status to its parent. So let's start. The behavior tree starts always from the root node. Let's start to create a simple graph. Let's create a sequence. The sequence is a composite node that you can create from here. Just right click to open this menu for creating nodes. And then let's connect the root node to our sequence. And then let's add a task so the agent can do something. And we can create, for example, a wait task. The wait task basically is a node that is executed and run a timer, and it basically continue to run this node until the timer is expired. At that point, it basically return a success message to the parent. And then the parent basically can based on its logic can do other things like executing other children for example as the sequence, or return the same message to the parent. In this case, the sequence, for example, is a composite node that execute in order of its children, because it can have multiple children. So for example, I can put another wait node here. And this one, let's change the timer. So we can put, I don't know, 3 seconds on this one. I can put 3 other seconds here and here. So basically, when the behavior tree is evaluated, it's evaluate the root and then go it run its child, that is sequence. The sequence basically start to run its children in order, so start to run the wait, and then until the wait finishes computation, it basically waits this node, and then when the wait finish, then go to the other wait nodes and so on until it reach the last one, and the last return the message, and then the sequence return the status message to its parent. So let's have a look how this one play in simulation. So to use this behavior tree on the agent, you need to create a behavior tree behavior component. So let's create this one, and then we can attach our behavior tree. So let's press play, and let's have a look. So let's select one of the agents, and then we are going to see what is going on there. Now pass there, and then the execution is finished because there is no other nodes to execute. Okay, so let me show you some other example. So now let's add a failure node. A failure basically return a failure message. Doesn't do anything, but it just return a failure message. And now if we try to let's save this one, try to play, let's have a look what will happen. And now we see everything finished. It's because the failure returned a failure message. Let's have a look if we can intercept this one. Okay, now it's almost 6 seconds. If we steps for every frame until we reach 6 seconds. We should see the return start of the failure. Yeah, sorry. Let's try again. Okay, let's try again until the wait finish. Yeah, as you can see, so the wait finish, so you see the green arrow, it means that return success, and then pass the failure, return failure, and the sequence return failure as well, because it's the behavior of the sequence. Okay, so now let's stop this. Let's have a look what you can do now. So now you have your logic, but usually you want to work on data as well, and so the behavior tree can store and custom data and access this data, so the nodes can read this data and also write this data. You can store this data in a blackboard. So you can create a new blackboard that is attached to this behavior tree. Let's go bb atoms and save. Now you have your here you can access the blackboard. In this blackboard you can basically add entries. So it's like a big table where you can store data and access this data by using name string. So for example, I can create a new bool data, bool. I can create a double. I can create object that store a reference to a real object. And you can, for example, create a vector 3. So for every entry that you add to the blackboard, you will see basically here you have the name of this key that is used by behavior tree to access this data stored in this entry. You can put a simple description, then you have the value here. So in this case, for a bool, a double, a vector 3. And then there is this special use metadata property. So you already know that in Atoms you can store data on the agents using Atoms metadata. Some of these metadata also control the simulation, like the position metadata, the state metadata, direction metadata, and so on. In Atoms you can basically link an entry directly to a metadata instead to use the internal value of the entry. And in this case, in this way, the behavior tree nodes that use this blackboard key to read or store data, they actually read the metadata or write directly to the metadata. So to link a metadata, for example, we can use our position metadata on the agent, and we can link to the actual metadata. So let's save, let's go back to the behavior tree, let's put in play. And here you will see the value of the entries on the blackboard, and you see that the position is changing, even if I'm not doing anything on this entry, because this entry is linked to the agent metadata that is using this behavior tree. Let's go back to our position. So with the link, you link the metadata, but there is also another option, the cache. In cache mode, basically the metadata at the beginning of the tick of the behavior tree is copied basically inside the data storage of this entry, the blackboard. So in this way, the nodes inside the tree that is accessing or writing this entry is accessing data that this entry store, not directly the metadata. But then after the tick is finished for this behavior tree, then the blackboard copy back the data store in the entry to the actual metadata. This is useful, for example, if you need to modify, to access and modify metadata using multiple nodes inside the tree, but each of the nodes, they want the original value of this metadata. They don't want work on the data that's already changed by other nodes. In this case, you need to use the cache mode. Now, let's go back here and let's have a look how we can use this blackboard data. For example, let's put a repeat node. The repeat decorator. So it's a decorator. So it's a node that has a single child that run that child based on some specific condition. The repeating node is basically a node that repeats a certain times, certain number of repeats sometimes its child, and you can set the number of the repeats here on the repeat times property. For example, if you want to repeat 3 times, this node will repeat this child 3 times. And if I delete the failure for now, let's put this one. Let's save. Let's have a play. So now pass there, go there, and now you will see that go back to the wait because the repeat time executes again its child when the child return the success message. So on, and then last time. And then stop. Okay, now you see that the repeat times are coded here, so it's not so dynamic. You can change, for example, during the simulation. But what you can do is to link a blackboard entry to this property. So let's create a int. Let's go repeat time. So integer, for example, we can put to repeat. And now we can select the repeat. And now if you go here, you see this little blackboard icon. If I turn on this one, then I switch this property to blackboard link mode. And now I can type directly the entry name here if you want, or you can use, for example, this menu to see all the entry that can be connected to this property. Now select, and then it uses my repeat times from the blackboard. So if I press play, now you see go on, then the second time, and then it should stop because we have repeat 2 here. And stop. In this way, basically, you can link basically to any property on each node. You can link a blackboard, and then, for example, you have the set blackboard entry task. For example, if you want to change a blackboard entry, here, for example, we can change the repeat time. For example, we can put like we need to change the repeat times, and this one is an integer, so we can change to, I don't know, to 5 instead. And now if I press play and change, now we see this one is 2. And then switch to 5. So in this way you can do dynamic behavior using the blackboard data. So there are different composites, decorators, and tasks that you can use. Have a look to each of them also in our documentation to see what each of these nodes does. Now let's go back to the behavior tree behavior module. Let's have a look to all the parameters that you can use here, the agent group. So you have the enable parameter. This one basically enable the tick of this behavior tree. Obviously you can control this using the blueprint, accessing the component, and then using the set enable and the set enable override blueprint function to access and modify this per agent if you want, or you can use the metadata. In fact, if you go here on the tooltip, you can see that you can control this using a bool metadata that has the name, the component name plus the @enable. And if you use this metadata, then you can control the enable directly by an agent metadata. Then we have a debug mode. The debug mode basically writes on the console the actual active stack of the behavior tree. You need to pay attention if you have a lot of agents, because this one can be quite slow to print all this stuff. So you will see basically the full stack that the behavior tree is running, and each step for each nodes and its result. For example, here I found the stack that already pushed this data, and then it said that this way node is still running, so it pushed on an active stack and so on. And this way you can debug all the steps for each tick for this behavior tree. Go back, remove. You can tick the behavior tree at specific interval instead to tick at every tick. This one is in seconds, so if you want to run the tree every half seconds, just put 0.5 there, and then the tree is only on 0.5 seconds. You can override this value per agent using the override here, or you can use the metadata as well as the enable. And then here you can choose when you want to run this behavior tree. The init frame, and the end frame. So init frame before Atoms compute the pose of the agent, end frame when it already compute the pose, but then you have the pre and post physics. Obviously you can have multiple behavior tree components to run different behavior tree. And then there is this blackboard slot here. So basically this behavior module basically run an instance of this behavior tree with the blackboard on each agent. So each agent has its own instance of this behavior tree, and this node basically use multiple threads to run the behavior tree instance for each agent on multiple threads. You can access basically the blackboard data of each instance by blueprint if you want. So for example, we can go to the level blueprint. Just let me stop this one. Let me access. We need to access the behavior tree. So the behavior tree component. So here we need to use the behavior tree component. Let's have a look. Yeah, it's a behavior tree behavior component, because the other one is the real one. And then from here you have basically you have access to the blackboard of each agent instance, so the global blackboard that I explained a bit. and also you can access the context, and here you can, for example, you can set actor on inside a blackboard entry, or we can set, for example, the repeats. For here, for example, we can go back to our behavior tree. Let's remove this one, and for example, we can set this one from blueprints. And sorry, let's go to the Beaver blueprint again. Repeat times, and this time, for example, 10 times. And we can connect, for example, on the, let's select the agent group, on the init, the pre-init frame, for example, event of my agent group. We can connect this one directly. And now compile. Before to play, we just need to set the agent ID here, because we need to set this value on an instance of a specific agent. So I can, for example, set on the agent 1. So if I press compile and play, now if I go here, you see now it's set correctly to 10. If I check the other, you see that is using the standard value here. So here, as you can see, there is the agent ID. If you put -1, then you are trying to access the global blackboard. So the global blackboard is the one that you can specify here. And for example, we can create a new blackboard. Maybe agent group, for example. Let's save here and let's connect it here. And let's connect. Where is my blackboard? Sorry, I created a wrong blackboard. So let's remove this one. We need to create an Atoms blackboard, not the real blackboard. Maybe agent group. You can see that the difference, there is this small icon. And then I can select my BB agent group. So the global blackboard basically is a blackboard, and single blackboard, and the behavior tree component create only a single instance of this blackboard for this component, and all the agent group can access this single instance. So it's a way to basically share data between multiple agents. So now basically I can add some data here on my agent group. For example, I can create an object, and we by, I don't know, pawn actor, for example. Save this one, and now if I go to the level blueprint, I set this one, set blackboard object value, and then I choose my pawn actor, and then get pawn, get player pawn, sorry, here, and then I set this one here, and let's select after this one, and I'll leave to -1 because we are accessing the global blackboard, not the one on a specific agent. Compile, save, and now to have a look, to check that blackboard, we can press play, activate the gameplay debugger, activate the atoms gameplay debugger, and then if I lock this one with the divide button and multiply button, you will see the global blackboard there, the BB agent group, and you will see the pawn actor that is correctly set to the pawn object there. So in this way you can basically set blackboard values specific for agents using blueprint. Obviously this one is exposed in C++ as well, as to access the right component. And let's have a look here. So now we explain all the property here. Let me show you a couple of really specific nodes in the behavior tree. So one node that you need to know is the lock node, the lock decorator. So the lock decorator is a decorator that guarantees that only one agent per time is executing its child. So for example, if you need to make sure that one node need to do stuff in a single thread mode, so you want basically lock any other agents until, you lock this branch for any other agent until one agent is finished with this computation. You need to use the lock. This is useful, for example, if you need to, I don't know, query the same query modify, for example, I don't know, the main blackboard, or I don't know, modify data on some other agents, or I don't know. It basically works like a mutex. So when it's executed, you lock the mutex on the entire component, and then when it finishes, you release the mutex. So this one is a lock that works on the component. Then there is another special lock that basically every node has, that is this lock agent. This lock agent, basically every agent in Atoms has a mutex that can be locked. And so if you turn on, for example, you turn on this lock, then it means that when the agent executes this node, he basically locked his mutex, and then when it's finished, release. This one is useful if you need to modify the same data on the same agent from multiple other agents. For example, if you need to modify, I don't know, direction and so on from multiple other agents, but you want the access and modify this data in a sequence order, that you need to use the lock agents. Then you have also another special node that is the run behavior. The run behavior can run another behavior tree, so you can create multiple behavior tree and run behavior tree inside other behavior tree. It's similar to the run behavior of the standard real behavior tree.